All right, so let's get started. Everybody's in the right spot. That's good. Let me bring up the chat over here. Okay. Okay, so last time we did sort of just a brief intro to the course, and let me get rid of, if I can, get rid of these toasts at the top. Okay. And so, so last time we talked about the introduction of the course and the basic idea of kind of the focus of this course and simulation modeling and so on. So we started to introduce a model, and we specifically said that we in this course are going to be using computer-based calculation or simulation tools to help us rapidly experiment with dynamical systems that we might see in sustainability, and these are going to be dynamical systems models, simulation models. And so we brought up this question, what is a model? And I kind of motivated that by saying, well, we know that these things here are often referred to as fashion models. And so why do we call them fashion models? And there are a couple of great answers in the class. One of the answers was that they've become these particular ways of looking, these body types, these ways of grooming and so on and so forth might be models for some sort of normative behavior. But initially, what the reason why these were called models is that they were meant to be what if systems for clothing. So when you're selling clothing, then the question was, somebody might say, what does that jacket or that dress look like on me? And it was too hard to tell by just looking at it on a hanger or on a shelf. And so they said, well, even if I'm not there present, if I at least see it on someone else, that helps answer the question for me, what if I were to put on those clothes? It may not be a perfect fit to my physique, but it's better than a hanger or folded up on a shelf. And so that's, here, what is a model? It's answering a what if question there. We talked about other types of what if models here. It's generally this idea that they answer these what if questions up here. So that's kind of the definition, the broad definition here, where when you hear the word model in this class, I want you to think that a model is not defined by what it's built of, but how it's used. And so anything can be a model, from an animal in the laboratory to some sort of abstract mathematical entity to a computer simulation. We all view these the same as models. And so you say, well, how does that work? And then we talked about this mouse model. And so we said in this mouse model, this is an example of where you might want to experiment on something that you would like to release, say, to a human population, but there are a number of reasons why it's intractable to test it on a human population. And so you look for a surrogate, a model that captures salient features of the system that you're interested in without having to implement directly on the system that you're working with. And so a mouse model might be, we might, say you might sleep deprive the mouse model and see how well it runs through a maze. And you'd say, if you notice a decline in how well it performs in the maze, that is a model of cognitive function in mammals who are sleep deprived. So the mouse is very different from a human in its lifestyle, its life history, its development, all of those sort of things. But as a first order approximation, we can say it's a lot better than a robot, it's a lot better than an insect, and so on. So we're not focused on making models that are perfect representations of the systems we're inferring and trying to make inferences about, but we're looking for things that get us there, to saying, what if we had sleep deprivation in a human population? Well, rather than sleep depriving a bunch of humans, it's more experimentally tractable to sleep deprive a bunch of mice. And so that's where that kind of term comes from. So with that in mind, if we looked at something like this, so we've got a woman who's on a treadmill, she's hooked up to a bunch of respirometry equipment, and so I guess I'm kind of interested in what you think. If you look at this, so we don't know why she's there, but what's your response to this? Is this a model system? I just explained how the mouse might be a model for a human population. Is this a model system? And if it is a model system, what is a model for? Any thoughts about that? And online, of course, you're welcome to put something in the chat, or if you'd rather unmute, I can also repeat things. So anybody have any thoughts on this? Is this a model system? Like the way the mouse was a model system? How many people say this is a model by a show of hands? How many people say it is not a model? Okay, so everybody seems to think it is a model. So if it's a model, what is it a model of? Yeah. So that could be, so it could be this is a model for the effect of exercise on the respiratory system. Yeah.
It could be like a model of the equipment on how well it responds to human biology.
How well, I'm sorry, which response? How well the...
Like how well the equipment works.
Oh. Interesting. So that's another sort of focus, is that we might focus, because I might have biased you by showing you the mouse model earlier. This actually could be a model of the exercise equipment. And so let's say you're selling treadmills, and so you need to stress test the treadmills. Well, maybe they're actually sort of amping up this human to run a lot longer. And so they're actually putting a stress test on the treadmill. So it's not actually a model of the human, it's a model of the typical types of stresses, or maybe over stresses that you would get put on the equipment. So it might be a model of the equipment. So that's kind of an interesting interpretation as well. And then this, people said it online, it could be a model of the cardiovascular system. So here, again, it's thought, it's here that this could be generalized to either from one piece of equipment to equipment that's out there. So what if we were to sell this exercise equipment, would it break down? What if someone were to exercise this way, would they pass out? Not this someone, but any someone. But it also could be that she came in for, maybe she was having a particular medical condition, and they had her come in to be tested for certain things that are associated with that condition. That, I would also argue, is still a model, because what they're trying to say is, let's say you feel faint certain times of the day. You come into the doctor's office, you might not feel faint. And so they're trying to say, well, let's model what's going on the rest of your day by experimenting on you in this limited situation here. It's more tractable for us to hook you up to these things and have you run on a treadmill. And yeah, you might only feel faint when you're going up and down the stairs, but maybe if we have you run on the treadmill, we can still model what's going on there to better understand that. So what if you were to exert yourself? And it's testing a hypothesis that it is the exertion that's causing you to feel faint. But instead of the scope of inference being all treadmills or all humans, then the scope of inference ends up being this particular human. So for this particular human, we're going to use herself to model herself in other contexts. So it's still not a perfect model for herself, even though she is, in the instrumentation, because it's not necessarily the context that they were interested in. So it's still a model, even when you're experimenting on the system of interest. I still argue it's still a model, because the experiment itself is always going to be artificial. And the reason it's artificial is because it makes it more tractable. Like, we needed to hook her up to this instrumentation here in order to actually get data out of it. So it's almost like an uncertainty principle. Like, the fact that we have to observe the system means that we have to change the system. But still, we try to make inferences about the system when it's not being observed as well. So that's kind of what we mean by, trying to give you sort of a broader definition of this model. Similarly, if you look at this, so this here, I'd ask a question, I'm just make sure I didn't miss anything online. This is an image of an intersection elsewhere in the world that has no traffic lights. And so there's a bunch of crosswalks that you can see. See if I can point these out with this pointer here. There's kind of a crosswalk here. There's a crosswalk up top of here. There's a hint of a crosswalk here, and there's one down here. And all the cars come in, and it looks like a mess. And that might be the first thing you take from it. But at least the first time I saw this image, I was kind of struck by that I didn't see any collisions. And if you look kind of closely, there's sort of a circle of traffic forming. It's kind of a self-organized traffic circle here. And there's even humans that are walking down the crosswalks over here. And they're having to make their way through traffic as well. So somehow the system is functioning. Cars are getting from one place to another, people are getting from one place to another, and instead of cars going straight through the intersection, they're somehow circling through here like some sort of self-organized traffic circle without something in the middle, roundabout here, maybe with a few people trying to take shortcuts. And this is by far, I mean, this is not a marvel of civil engineering. I don't think it's meant to be an example of that, but it is illustrative to me. It is interesting to me. This is, before looking at this image, I would have never expected that this would be a possible outcome of getting rid of what I would assume, like in a busy intersection like this, would need traffic lights. But at least in this part of the world, for whatever reason, you get rid of the traffic lights and this thing self-organizes and traffic still flows, and people apparently, I don't get into as many, they may still get into accidents, but at least there is a possibility here that they won't just crash into each other immediately like I might expect them to be. So this in itself is a model. It helps me answer the what if question of what if we got rid of traffic lights? And I'm not saying this is a generalizable model. So if you implemented this here in Phoenix, it might not work. There might be other aspects of the model, other assumptions that I don't see. And so just like if I go back to the woman on the treadmill, if I were to make inferences about the human cardiovascular system, I probably need to have more than just people who look like her. I probably also need to sample from men, probably need to sample from people of different races and ethnicities, different ages, and so on, in order to generalize. If I just experiment on her and call her the prototypical human, then I might end up having results just like these that may work in one context, but don't work in a lot of other contexts. Interestingly enough, a lot of medical research in the past couple of decades, and it's changed a lot recently, focused on men. And then they would claim that the reason that they only use male subjects is that they were worried about the menstrual cycle affecting the outputs, so that there you get these sort of weird irregular peaks, and they'd have to control for timing of the menstrual cycle and so on and so forth. So for some reason, it would be better to work with men. But then when they actually looked at the physiology, when they actually looked at metabolites from the bloodstream and all that, they found that in a lot of these experiments, the women had much more stable outcomes, physiological indicators than the men, perhaps because this cycling was making them a little bit more homeostatic. And so your guess about what's going to be the best model system can often be wildly wrong, and itself should probably be a hypothesis that needs to be tested before you can take it for granted. And so that's the reason why now medical research tries to be, sample from a wider range of the population and help control for things like sex, ethnicity, gender, et cetera, all those things. So, so we have to be careful about generalization, but still, even with a special case, we still learn something from it. And that's really the whole thing about a model. Is it illustrative? Is it insightful? That's really what a good model is. The Titanic, I talked about this last time. The Titanic was a model system, even though it wasn't intended to be. It wasn't intended to crash. When it sank, they originally thought that it crashed into a very giant, iceberg, and it was so massive and so on and so forth. Well, then later, decades later, when they're looking back at the data, now they think that actually the frigid cold water changed the metallurgical properties of the material that the boat's made out of, and made them more brittle, so that even something that you might expect the ship would just plow on through could actually cause it to shatter and sink. So so they learned a lot about about building these giant ships from this process here. Now, the people, so in some ways, anytime you engineer anything, you're experimenting on the people using that thing. But the people that are taking place in that don't really give their informed consent. If I want to do an experiment, if I'm in my research lab, if I want to experiment on anybody, even if I wanted to run an experiment with you, because it's a federally funded university, so that it gets federal dollars for a lot of the research projects, I would have to make sure that all of you gave your informed consent to be a part of my experiment. If you're privately funded, like a Facebook or like a cruise liner or whatever, you don't have to, people don't have to give their informed consent. They don't realize when they're taking part in an experiment and when they're not. And then arguably, they're always taking part in an experiment because there's always things that could happen that you could learn from. And so we don't always, when we are deploying policies out on cities or technology that people buy, we are experimenting on those people who are not giving their informed consent. But I can guarantee you, if anything interesting happens, we're going to learn from it. And that might benefit the future, but at the cost of the current. So that's a big reason why we look for these surrogates, because we would ideally not like to focus our learning on the real systems. We kind of want the tuning to go on in the real systems and the major learning to go on in our surrogate systems, like we build in the laboratories and on the computers and so on. So yeah, the mouse didn't give its conformed consent, neither did Kate or Leo, but we learn a lot from them. But there's a reason why people tend to focus on the mouse, because for whatever reason, the mouse tends to be a more acceptable loss than poor Kate Leo. So yeah, now another nice kind of more concrete example of that is back when I was learning how to drive. I was born in 1981. And so back when I learned how to drive, we had there was the introduction of this thing called an anti-lock braking system, which now is commonplace in all cars. And so before the ABS, if you were to stop fast, you had to put your foot on the brake and pump it. And the reason you do that is if you just slammed your foot on the brake, your wheels would lock up and you'd stop rolling and you'd start sliding. And so if your wheels were locked, once you're sliding, it doesn't matter, what you're doing to the brake calipers because your car is just sliding at that point. So to prevent sliding, you were supposed to pump your brakes. And then that way you'd have a little bit of stopping, but you wouldn't get into a slide. And then you'd release some of that, and then you'd start the process all over again. And so when you were driving, you had to learn how to pump your brakes. That was the only way to stop fast. Eventually, they realized that you could implement an automation system. So you could build a car that would be able to pump these brakes for you. And so they started selling cars, and now all cars have ABS, that when you slam on the brakes, you just put your foot down. And then if you've ever heard kind of a hum that comes out if you ever slam on your brakes, you hear kind of a, that is, it's automatically pumping those brakes to keep you from getting into a slide condition. Now, when they first deployed this, the mental model of drivers was that this was not going to work as well as humans pumping the brakes. They said, no, I know how to pump my brakes. Because the thing is, if you bought a car with ABS, you couldn't pump your brakes anymore. If you pumped your brakes, it would be like the worst of both worlds. So you had to just put your foot down, and people were taught they had to pump their brakes. And so people thought ABS can't do as well as me. And so the fear was, if they bought a car with ABS, there would be an increased risk of front-end collisions. Now, interestingly, when you actually look at, here's a paper that studied it, after ABS was deployed, there were more collisions immediately after ABS was deployed. But when you look at the data, the cars with the ABS were not in the front-end collisions, they were in rear-end collisions. They were getting hit. And so it turns out that what was actually happening was that these cars with ABS were stopping much faster than the cars without ABS because they could brake better than the human drivers. And so this was an example of what the real problem was, that in order for ABS to actually be safer, everybody had to be using it. If you only had 10% of the people with ABS, they actually they would stop without ever hitting anyone in front of them, but people would plow into them because the people behind them were very likely to not have ABS. So this was an example. They had to update the mental model after this real world experiment to sort of say that when we deploy a technology like this, there needs to be a minimal level of penetration for the technology to actually end up realizing the gains there. And so now that all the cars have ABS, they all stop around roughly the same, and we're back into a better world. But there was that transition region where there were too many human drivers, and they were screwing the whole thing up. So it was kind of an example of this cyclical process of model building where you're taking mental models, you've got experimental models, you go into the real world, you take that data, and you update your mental model again. And that's kind of what we try to do with the simulation models as well. We learn something from sim, we take that, we update our models inside our heads, and we keep going. Now, so what other things can be models? I'd argue that even pictures can be models. So this is a model of a beaver tail cloud formation. You're like, well, and if I look at that, it looks really similar to a bunch of other cloud formations. So if you were to ask somebody, well, what's a beaver tail cloud formation look like? Already in the words themselves are kind of a model that tell you something. But if you just show them a picture, you say, oh yeah, I've seen one of those before. And so, so the picture itself can be a what if. What if you were in such a weather event? What it might have looked like. Same with the wall cloud. What is a wall cloud? Well, I'll show you a picture of it. Oh, I've seen one of those before. What you've seen before was probably didn't look like, if you really look pixel by pixel, would look very different than this. But the picture itself helped you generalize and connect to that. So if I were to look at all these beaver, you can look, all these sort of have, this here, even though it differs in microscale ways, it sort of tells you something about these different formations so that you can spot them now that you've spotted one of them. And now sometimes the generalizability doesn't work out so well. So these don't look quite as much like that. And so, again, there's always the strain of generalizability in any of the models that we build. Words can be models. The word funnel cloud combines the notion of a funnel with the notion of a cloud. So without even seeing what a funnel cloud is, hearing that word makes it so that if you ever saw this, you'd say, oh, that looks like a funnel cloud because it reminds me of both a funnel and a cloud. So, it is, that seems weird, but a phrase can be a what if model. What if we were in this sort of weather situation? Well, you would see a cloud that looks like a funnel. So a lot of things can be models, but more practically, the things that we'll work with when we look at data and so on are things like graphs. So graphs themselves can be models. I can have data, like these are data points taken from high school GPAs and university GPAs. Every point is an individual with their high school GPA matched up against their university GPA. And I forget what population this is. Doesn't really matter too much, but they fit a line through it. And that line kind of gives you the impression that there is a correlation between high school GPAs and university GPAs. And so this is a model. We aren't saying what the causative factors are. We don't know why this relationship exists, but this suggests that you can ask the what if question. What if somebody with a 3.5 high school GPA entered college? And this model would suggest that they're probably going to have around a 3.5 GPA in college with some variance. And so this gives us a model of that. So graphs themselves can be modeled. And those graphs don't even have to have data. If I go back to an exercise example here, this graph down here on the bottom, has a bunch of these red dots, which aren't real data. They just added the red dots as a way to sort of imply that if there was real data, if we did put someone on a treadmill and we measured their oxygen consumption, that's what's on the y-axis, their oxygen consumption, and we put them through different levels of exercise intensity, we would expect that the data we gathered would be close to this line. So the points themselves are already themselves kind of a model of what we would expect. And they're saying they'd fall close to this line. And so the line really is the model that they're communicating. And that model is that we would expect that if their exercise intensity increases, their oxygen consumption will increase until a point where after that point, their oxygen consumption stays flat. And we call that point VO2 max. Now, we're not saying this is correct, but we're saying this is a model of what this one is, what somebody is hypothesizing is going to happen. And so this is something we could look for here. So this is without, I mean, you could write all of this in words, but just showing you the picture communicates so much about what if you put somebody on a treadmill and put them through this different level of exercise intensity. So graphs themselves can be models, just like this graph up here kind of goes back to that example that I ran through last time with, in that case it was wolf and moose, but it's the same idea, where there could be situations where you get these oscillations in both predator and prey populations, and that's being communicated through a graph. So again, really anything that helps answer a what if question, regardless of its form, is what I call a model. And we'll focus on simulation models, models that are built out of computer code. But really, when we talk about models, really anything could be models, just so long as they're being used to help answer a what if question. Okay. So, so any questions about that? Is that definition clear? But I don't want you to think model must mean math. I don't want you to think model must mean simulation. I just want you to think model is a what if question. And so it could be a physical object in front of you. You know, what if I had a bunch of gears and I put them together in this particular way? Well, that's a model of what might happen if you generalize that experience to other mechanical objects and so on. Questions online? All right, so with that, so let's think about it here. So there's this phrase model citizen. Where does that come from? What does that term model citizen mean? Does anybody have an idea? Yeah.
Somebody that follows the law and faithfully that's it.
Okay, so the answer there was somebody that follows the law, and I'd like to unpack that as to why we call that a model system, but I've got a couple of answers, so I think we can probably pull all those together. So yeah, I saw your hand first.
Yeah. I think model in this case is supposed to be synonymous with ideal, but we just use as like a model of an ideal system.
Okay, ideal, following the rules, ideal. Okay, we got those in mind. Go ahead.
Like a citizen that does everything right, like follow like everything in model, like citizen should do.
Okay, so we got follow the rules, ideal, everything a citizen should do. What makes these definitions answering a what if question? I guess, like, so why would we associate those definitions with the term model citizen? What's being modeled? So when you think about a model citizen, does that change the way you think about your own behavior or other behaviors? Or because I guess the idea here is, I heard the notion of right, whatever right means, whatever ideal means. I mean, there's a bunch of different behaviors that any citizen could do, but a model citizen here seems to suggest that if you really call yourself a citizen, there are certain things that we expect you to do. So what if I was a good citizen? Well, if I was a good citizen, I stop at red lights. I don't go through red lights. So that's kind of so the what if here is, you know, what if I were put into these situations? What would a model citizen do? WWMCD, I guess. So the idea here is this can be prescriptive on what you as citizens might do. Now, that doesn't mean you always do them, just like on those VO2 max graphs or the graph of high school GPA, there were outliers. There were things that strayed from the line. So you don't always necessarily stop at red lights. You don't always follow the speed limit. You don't always, you know, follow the rules exactly right, but you try to. And so this is the ideal. That's that word, that ideal, came up there. Now that's one way to view this. You say, well, what is the utility of having this? I see some question or some comments on here about effectiveness, behavior. The term results to an optimal result. Online optimal result. And so that kind of gets to this too. Like, well, so what do I mean by optimal? Another way to view as model citizen is we sort of want a certain something out of society, right? We all want to be happy. We all want to be, you know, maybe happy and healthy and all these sorts of things. Well, you'd have to say, well, how do we make a society of people all feel that way? And that's a really hard problem, because everybody's got different wants, different needs, they behave different ways, and we need to count on certain things. And so what we might say is, well, if we can count on certain behaviors, can we end up developing policy that can help make the group of us behaving that way, you know, maybe in favorable positions? And so a model citizen can also be viewed as, what behaviors do we need in order to get our societal goals to be met, assuming some model of how society works. So we assume that if everyone stops at red lights, then if we set up the traffic rules just right, then we can make traffic flow efficiently. We have to make some assumptions. And the assumption is that everyone's going to stop at the red lights. If they don't stop at red lights, then our whole model of traffic goes down the drain. So model citizen is in some ways prescriptive on what we want everyone else to do, but it also can be descriptive of if everyone were to behave that way, what do we expect to get out of the group as a whole? And that goes to this kind of optimization idea. So that's sort of, so I just want you to think, whenever you hear the word model in everyday speak, I want you, for at least during this semester, to sort of think about it through this what if lens. What is really being communicated when someone uses that word model? All right, now I've mentioned this before, but there's assumptions. Like I said, the last thing is all about assumptions there too. And the models have the GIGO property, garbage in, garbage out. And so a model is only useful as its assumptions are realistic. If we want to make inferences about human physiology in general, then we probably need to have a diverse pool of people that we're sampling from in order to make inferences across a larger group. And so if we don't have kind of the right individuals we're sampling from, then we probably won't have physiological results that will necessarily work with everybody in society. This example of the fashion models I thought was a good one, because the general idea of putting clothes on humans to make the clothes more illustrative or of what they look like is a good one. But who you choose to be the fashion models affects how the fashion is looking. And so if you're trying to assess one jacket over another, now the stakeholder has to be savvy enough to somehow factor out any residual sort of effects that come from the model choice itself, because we shouldn't care who the person is that is modeling the jacket or the dress, but we can't help it. And so if people are trying to sell us a jacket or a dress, they will explicitly put people in there that will confuse us. We will say, yes, it makes sense that you put that jacket on a male, and me as a male, I want that jacket because I think it looks good there. But it turns out that I'm going to need to put far more product in my hair. I'm going to have to lose a bunch of pounds. There's a bunch of things I'm going to need to do to look like the image there. I am not going to look like him if I put that jacket on, even if I want to look like him. And so, this idea here is that maybe that jacket just isn't for me. And so evaluating the jacket requires the right assumptions. And maybe he doesn't really, assuming that I look like him, maybe are bad assumptions. And so that's when garbage in, garbage out. Even if you build a beautiful simulation model, if you parameterize it wrong, if you sort of put the wrong birth rates into your model, if you put the wrong rates of how much water people use, if you put, how much global warming we expect, all of these different things, if you get those parameters wrong, then a beautiful result in your sim is not going to mean a beautiful result in reality. So we have to get the assumptions right. So models are always going to be wrong. The question is not whether they're perfect, because they're not ever going to be. The question is whether they're useful. So the practical question is, how wrong do they have to be to not be useful? And that's something that we're going to see as you're going to build models, and there's no way you're going to make them perfect. But if you tweak them in just the right ways, you'll make them informative. And that's what we really kind of are shooting for there. So any questions? Let's have a question on here. So there's a question, is that why we have standard deviations? And so I think that question is referring to like when we see estimates of performance, people say plus or minus a certain number of standard deviations. And yes, that is sort of an example. That's partly also due to stats. If I sample 10 people and I'm trying to make an average, like I want to say, how do people feel about mask wearing? Well, I could ask 100 people that, and I might get a certain proportion are for it and a certain proportion are against it. If I want to make an inference about the rest of the population, I'm using those 100 people as a model for the rest of the population. And statistically, in order for me to estimate the population mean from a subsample, I have to put confidence intervals around it. And those confidence intervals basically say the real population mean is very likely within this large interval. It's not the point. So these 100 people, maybe there were 60% for masks and 40% against, but the confidence interval might go from 45% to 85%. And that might mean that the population as a whole is probably not lower than 45 and probably not higher than whatever I said, 75, but it's probably somewhere in between. So yes, the confidence intervals help us quantify the uncertainty we get out of models. That's one of the ways we can quantify that. So that's a great question. Any other questions about this general framework? Okay. All right, so let's skip this attendance question for now, just for time. And all right, so today the new stuff is recognizing the kinds of different models. And so the first thing I really want to focus on are our mental models. And so I've put an image up here. I'm not going to say much about this image, but now I want to hear from you. When you look at this image, what are some of the first things that come to mind? And so you can put it in the chat if you're online or in person here. You can raise your hand. What do you see here? What are your first impressions when you look at this image? Yeah. A brand logo. So some sort of potential brand that you're kind of associated with. You don't have a particular brand in mind, but you say it kind of looks like a brand logo. Okay. Any other? Yeah.
The first thing I see is, like, even though it's not technically there,
so I hear that there is potentially an upside down triangle, which is recognized is not actually there, but you feel like it's there. Yeah.
You said about the upside down triangle, it looked like that Star of David.
So I hear the Star of David. And so I think the idea here is that even though there isn't a line forming a sort of six-pointed star, you can kind of follow it around. Online, I see some comments about Zelda. I see different shapes and symmetry of them. Sort of looks like shapes that are cohesive together. Yeah, a lot of people are saying Legend of Zelda, Ocarina of Time. So a lot of comments about Zelda, which is actually the first semester anybody said anything about Zelda with this one. Anything else? Any other thoughts? There's another video game which normally comes up in previous semesters. Yeah. Pac-Man, yes. So in fact, there's two classes I show this slide in, and the other version of this class, somebody said not only Pac-Man, but she said, I see 3 Pac-Man and they're entering a room where there are ghosts that are hiding under a table, or they're about, she had this whole narrative that she saw just from this whole thing here. So she got a lot from just looking at this image. Now I think that, yeah, so Pac-Man also came up online there too. And so, but what's I think great about it is formally, really, there are no circles, there are no triangles, there's very little of the things that we say we see formally on this image here. And so, you know, like there's no white triangle, there's no black triangle, there's no circle here. We think that there might be a circle with a triangle on top of it, but that is our mind trying to come up with a causal story for how the heck this happened. So we have mental models which help us answer what if questions about what if you were to put a triangle on top of another triangle. And this is an output that's consistent with that model. You know, what if, you know, you were playing Pac-Man and this were sort of the outcome you would get, and then what might, so there, we make these inferences, but they're built on not what's written on the page, but the experience that we've collected over our entire lifetimes, built up in our mental model. Similarly with this one here, does anybody have any comments about this little cartoon that's drawn there? What are your reflections? Yeah. Pink Panther. Okay, Pink Panther. So it's like there's, you're saying this like saw is like cutting out somebody from underneath? Pink Panther's going underneath. And what shape is Pink Panther cutting out? A circle. That's interesting. How many other people see a circle being cut out underneath Pink Panther? Okay, so a number of people, or not, yeah, not underneath, but online and see any other comments about this. Yeah.
Looks like you really observing what you talked about.
I see. So
Using that, like you're like taking advantage of the fact that you get distracted and just getting out of the
interesting. So a lot of really great inferences about that, that this image is an image of a person who is really distracted, maybe distracted by himself, so interested in hearing what he has to say that he's not noticing that something's going on underneath him that maybe he should. So, which is kind of interesting too. Any other thoughts about this, or disagreements or agreements? Well, I mean, I think it's interesting about this is, for one, the fact that I think we all look at this and see a man. I mean, this cartoon is, if you actually compare this, there's no person on Earth that looks like this, right? I mean, if I were to take off this mask, I mean, I have kind of a large nose, but nobody has a nose that goes from their mouth to their neck, right? You know, that's like Roxanne level kind of, you know, Cyrano type of thing. So that, you know, that's like the proportions are all wrong, and yet we know that this is depicting a human being. We know that based on the clothes, based on a bunch of other things there. It has all the right features. So it's not perfect, but it's clear that's what this is depicting. We all see, I think it's pretty easy to see a circle here, but I mean, if I put my arm here, I mean, my arm is from my elbow to my tips of my fingers, I can't even get the whole way this way, but I can easily cover that here. So it's an oval drawn on the screen, but we all kind of know that, well, we're probably looking at an angle, and so that circle is going to look spread out. So we don't actually know if it's a perfect circle, but we assume that it's probably a circle because if you're going to cut a shape out, it might as well be symmetric. So, you know, so we assume it's a circle, right? We have a bunch of these mental baggage that we've built into our perceptions to try to understand what we see. And that mental baggage is built up over time. If I asked a 2-year-old or a 4-year-old, I might get a very different answer about this. You know, you had to know what this thing was. You know, this saw here, if that's really what that is depicting. You know, I mean, so these things you end up using. These are things that a computer is not going to have, but a human being will. Similarly, if I look at this one, so this is sort of a famous painting. I think you can find this in the Louvre. And so this up top here, this says tandem convergent. This is the model for fiancés. This is tandem divergent. This is a model for a couple just getting into a divorce. And so if you look at it, this is a bicycle with 3 wheels where the front wheel of these 2 bicycles are joined together. This here is the same sort of idea, but it's the back wheel that's joined together. And so when I look at this top one, I realize this isn't really about a bike. This is about the feeling you get when you're with someone that you want to be with for the rest of your life, and you just want to be closer to that person. And no matter what you can do, you can't get any closer. You're up against a rock where you're as close as possible and you still want to be closer. And, you know, that's kind of what's being communicated here. Whereas if you're coming out of a long relationship, it's exactly the opposite, where you want to be nowhere close to that person, but you're stuck being with that person. And that's very much what's kind of going on here. I know this is evocative to me. When I look at these images, I think about the first time I fell in love. You know, I think about the first time I was in one of these sort of situations. Unfortunately, not my current marriage is nothing like this, but this is clear to me. And I know it's not about bicycles, but I don't need to know a lot about bicycles, but I kind of need to know enough about bicycles to really get the message. So there's a lot going on here. I don't have to build these bicycles to get the message. These bikes don't exist. Well, now they do, because somebody actually took this and they built the top one. So you can actually find a physical version of this, but you didn't have to build it to know what was being communicated. You know, so this sort of thing, you know, I have mental models that help me process these things. Likewise, you know, if you think about this boat here, you got these 2 people sitting in a boat, and this back guy's got his hand on the sort of rudder where the engine is here. The first time anyone's, you know, if I were to ask you how to drive this boat, if I wanted to turn the boat to the left, then should I turn the rudder to the left or the right? How many people would say left? So I want to turn the boat in your way. I want to turn that way. So then do I grab the rudder and pull it this way to the left or this way to the right? So how many people would say left? How many people would say right? So I think most people here are saying right. And the thing is, you might have to kind of think about it in your head, because the direction here is reversed from where you might expect. So in a car, if I want to turn left, I turn the steering wheel to the left. But in the boat, if I want the boat to move to the right, I actually have to push the rudder to the left and vice versa. So the back of the boat, the steering direction is reversed from the front due to the mechanics of how this is set up. Now, the first time you get in that boat, you don't have to think through the mechanics, you just try it. And if the boat goes the wrong way, you just flip it around and your mental model updates. So you don't actually have to work out the math, you just go through the experience, and the experience changes you. It's a plastic deformation. And then from that point on, you know how to drive the boat. If you ever watch the movie Independence Day with Will Smith, he's getting into an alien ship, and somebody's put the diagram of whether you push forward on the throttle or back in order to get the thing to go forward. And he reads it, says, okay, I'm a pilot. It says to go forward. So he pushes forward and the thing goes back into the dock. And he says, oh, some jerk, they got it backwards. He flips the paper around and then he goes and he's up and running. So then he pulls back and he takes off. And that's very much kind of what goes on here. So we have mental models that help us engage with the world. As we engage with the world, we update those mental models and then further engage with the world. So I think this is my last example of this. So this is kind of a famous narrative to illustrate these ideas. And it's been studies and all that, and people sort of survey people about this. So I'm gonna just read this out loud here. So a man and his son are driving in a car one day when they get into a fatal accident. The man is killed instantly. The boy is knocked unconscious, but he's still alive. He is rushed to the hospital and will need immediate surgery. The doctor enters the emergency room, looks at the boy and says, I can't operate on this boy. He is my son. Now, even 5 years ago, when I'd give this example, I would have people who would be puzzled by this outcome. But over the last maybe 1 or 2 years, whenever I give this example to students, there's always someone who sees no puzzle whatsoever, doesn't understand why there would be a puzzle. So let's sort of say, like, can somebody explain how this doctor could say that this boy was the doctor's son? Yeah.
Morning.
Right, so I heard boy's mother, I heard same-sex couple, another father. Online, I'm sorry, somebody unmuted and said, what were you about to contribute there?
Oh, I was gonna just say that it was his mom.
His mom, so you're the mom. In the chats, I see mom, I see other parents. And so yeah, both of those are options that, this could be a female doctor, or this could be another male doctor in a relationship between two men. Now, this example has been, they've used this example for decades, and decades ago, you'd read this, and people that are maybe from, I don't know much about exactly the demographics of your ages, but just guessing, maybe people around, say, your parents' ages, or maybe a little older, would read this, and they'd be totally puzzled. They just wouldn't get it. Because they grew up in a world where doctors were all men and relationships were all heterosexual. And so they've built a mental model of what it means to be a doctor. And this does not fit within that model. And they just completely are confused by it. And so younger audiences here don't seem to see much of a puzzle. That response comes very quickly. Oh, it could be a mother. It could be another male father. No big deal. So so these mental models are definitely guiding how we interpret information from the world. The question you have to ask yourself is, how useful are your mental models, and when do they need updated? Because clearly the modern world is such that this shouldn't be a puzzle, but still there are people who didn't grow up in the modern world. And so they have mental models where, this doesn't make any sense to them. So you have to sort of always kind of reevaluate, do I need to update my mental model? All right, so that kind of gets us to our general description of mental models. Tremendous store of information, really super valuable, driving a boat, processing the bicycle and all that. That's really the strength of mental models. But the weakness of mental models is there are some, and there were some people that responded online that they said they actually didn't, they bravely volunteered that they actually didn't see the solution to that. So I appreciate that, volunteering that. So the weaknesses of mental models is they're unreliable at handling complexity and dynamic change. And so we want to use mental models sometimes, but there are certain problems, especially problems where things are changing over time, when there's lots of parts, where maybe the mental model is not our best choice for investigating things. And that's the reason why we implement, or we then turn to quantitative models. And that's what we learned to build in this class. So in a quantitative model, they're much better at handling the dynamic complexity, or the complexity and dynamic change, having multiple parts and all those sorts of things. The downside is they really only incorporate whatever information you put in them. They don't grow over time. They don't learn. They don't have the tremendous store of information. They might be built on poor assumptions. You can build a model of a hospital where all of the doctors walking around the hospital are men. And if an architect is using that model, then they might, only install male restrooms. So, so I went to school at that time at the largest university in the United States. Now that's here at ASU, but at that time it wasn't. And there were old buildings on campus where one floor would be all male restrooms, on one floor would be all female restrooms. And that was because initially, because they were engineering buildings, and my background was in engineering, they had all men's restrooms, and they had to renovate, but they didn't have room to put 2 restrooms on each floor. So they just said, all right, well, every even floor will be the women's restroom, and every odd floor will be the men's restroom. And that's because they built that with a model where all engineers are going to be men, which wasn't a good model. So so the assumptions you put into models still matter. So you still have to be careful about that. But when you're thinking about dynamic complexity and change, then that's where these quantitative models can come into play. So we're learning to build these types of models. So what are the types of quantitative models, and what are they used for? Well, we're going to use quantitative models, or at least talk about their use, for 3 different purposes: inference, prediction, and narrative. And what do I mean by that? So for prediction, this is like when you wake up in the morning and you want to know what the weather is like. Well, they use sophisticated quantitative models to look out at the weather conditions and then make a prediction on how the weather is going to be throughout the day, maybe throughout the rest of the week. So in this case, this is a very traditional form of quantitative modeling. You take data, you can combine it with historical trends and maybe some mathematical kind of first principles, maybe some physics, and then you try to forecast outcomes into the future. So we're not trying to learn anything about the systems. We assume that we know enough about the systems already to guess what's going to happen in the future of those systems. So that's what I mean by prediction or forecast. The other thing that we can do with quantitative models is inference. So in this case, we're learning about systems by doing experiments in the real world and then trying to then make sense of those experiments. I can sample the GPA data, the correlation between high school GPA and university GPA, and I might not know what the relationship was, but after I sample it, then I can build a statistical model which helps me learn about these things, which might tell me that, helps me investigate hypotheses that maybe students that are better prepared are going to, in high school, will be better prepared in college. Or maybe, there's another explanatory variable that I'm not seeing here that has to do with financial background or something like that. And it turns out that that background, how well supported those students are financially, predicts both of these outcomes. So I can make inferences about causal variables through this. So inference is looking at data and then building models to try to understand relationships more generally so that I can actually combine factors together. So like effects of socioeconomic status on educational attainment, et cetera. So that's what I mean by inference. Now, the last thing we can do with models is narrative, to tell a story. And so back when Obama was president, then there was a major economic downturn, and Obama wanted to put a recovery plan in, which he ended up doing, but he needed to convince people of the recovery plan. Now, he can say that the recovery plan is going to do X, Y, and Z, but instead they put together graphs like this one. So, and they use quantitative models to generate these graphs. And these graphs basically are two lines in this graph. The dark one on the below is with recovery plan. The lighter one on top is without recovery plan. And the y-axis is the percent unemployment rate. And so here they're trying to say, in some ways it's a forecast, but really they're not trying to forecast. Like when I'm trying to plan what I'm going to wear for the rest of the week, then I really care exactly what the number is going to be on Friday, for whatever the weather will be. But here they're not saying that, for sure things are going to be this percentage, but they're saying here that look how much better things are going to be if we do with the recovery plan. They're trying to communicate the impact of the recovery plan more visually in a more salient way than they could in words. Similarly, I can show a model. This is, I think, 100 years, roughly 110 years on the x-axis, and CO2 levels on the y-axis. And there are three different lines being plotted here. There's the CO2 in Antarctica, the CO2 in Hawaii, and the CO2, and then they've got the global temperature. They call the global temperature anomaly. So the red line is the temperatures, and so the temperatures are on the y-axis on the right. So temperatures are over here, and the CO2 levels are plotted over here. And what we can see here is that if you scale things correctly, then what you see is that the temperatures and the CO2 are dead on locked with each other. And so that tells a story that sort of is more convincing that there is a relationship between CO2 emissions and global temperature rise. And so we're using a quantitative model to try to be convincing, to tell a story, to communicate to others. Now, again, the models can also be used to deceive. So we could zoom in on particular regions of this plot, like down here. And so from this region here, it looks like there's no relationship between these small scale fluctuations in temperature and CO2 rise. In fact, there might even be an opposite relationship. And so when we zoom in on this area, then we'd say, look, there's no relationship there. We needn't worry about CO2. But in reality, that's where it's kind of like putting the jacket on the ill-fitting model, is that this is not a generalizable trend. If we go backwards and we zoom out, then we'd see actually the generalizable trend is that there's more, these two things really more track them, especially out here, they track themselves a little bit better. And so this is an idea of how models can also be used to deceive. And so we need to be cognizant of this and always are willing to ask the question, okay, so what assumptions were made? How well does this generalize, and so on and so forth. All right, so any questions about those three uses? We've got narrative, prediction, and so narrative, prediction, and inference. Those are three ways we can use quantitative models. Questions online? Okay. So then there are three types of quantitative models, and we're primarily focusing on the third type in this class, but I want to be able to recognize the others. And so the first type are analytical models. So these are the mathematical models. These are more like what you would kind of do by hand in 211. So this is a model of disease spread in a population, SIR model, which I think most of you probably are familiar with from like SOS 101. Number of susceptible people, number of individual or infectious people, number of recovered people, and ways in which you get flows. If you have a lot of infectious, how does that affect the future number of a lot of susceptible, how does that affect the future number of infectious? A lot of infectious, the future number of recovereds. So we can mathematically model these things, obscuring all the details about how people bump into each other and those sorts of things. So it's a very simplistic model, but it provides exact solutions. And so this is something where we can put parameters in. So, how infectious is this disease? How quickly do people recover? And we can get exact predictions out about how long the disease will be around, assuming it doesn't change or something like that. Now, the trouble is that some of the predictions that come out of it are maybe difficult to solve by hand. they are a poor communication tool. So this is a steady state solution, we would say, of this model here. And this is not something that a stakeholder is going to be very receptive to. It's really ugly. It doesn't really tell you much of anything. And it often can describe what happens at the equilibrium. So this is describing the kind of herd immunity case, but it doesn't tell you what happens in between. And that's often hard to get with these models. And so analytical models are good for back of the envelope calculations of long-term effects. They're not so great for understanding the fine scale things that happen as you get there. So for that, we have numerical methods. And so you can build these into spreadsheets, for example. And so these cases, you're not going to do the math. You're going to describe things almost more like a balance in a checking account. You're going to sort of know, if it was an SIR model, how many susceptibles, infectious, and recovereds do we have any particular day? And we can then predict how many we would have the next day, and so on, and then plot those things out. And we look at those plots. And so we're not making a claim about the mathematical form of what these are, but we're looking at the trends over time. So numerical methods are ways where we get rid of all of the mathematical certainty to allow us to examine things at a smaller time scale, but which is good. And it's a better communication tool because the outputs are plots. But the downside of that is these are approximate solutions as opposed to the exact solutions we get in the math case. And there's not a lot of flexibility. It's hard to, if somebody asks for a major change in the way the system works, like, well, what if people didn't recover? What if they had a period where they were just exposed? What if they could get reinfected? It takes a lot of work to update this spreadsheet to make that work here. And so it ends up not being a very flexible solution for exploring these other scenarios as we move forward. So that's where we get to simulation models, where this up here is an example of an SIR model implemented in a tool like we're going to use in this class, where it's very clear to see the model. It's got a box for susceptibles, a box for infectious, a box for recovered. It shows how things transition from one to the other. If you simulate it, it can generate graphs like the numerical model. But what's cool about it is that if you need to make some changes, like to add other compartments or make it so that the recovereds can then become susceptible again, it's very easy to make these changes. And so it's still approximate solutions, like in the case of numerical models, but you don't have to be explicit about the numbers, it's much more flexible. The downside is the tool, VinSim or InsightMaker or whatever, makes a lot of decisions for you as it takes the image that you've drawn up here and it turns it into, behind the scenes, a numerical model like I had on the previous page. So it often depends upon unknown or complicated decisions by the person who wrote VinSim and all that. So now you're kind of in a joint process where you're trying to build a model, but your modeling decisions are modulated by decisions made by the software developer who developed the simulation tool. So that's and there are a bunch of different simulation methodologies. And so the three big groups are agent-based modeling, discrete event system simulation modeling, and system dynamics modeling. And so I don't want you to necessarily memorize all of these sorts of things, but the one that we focus on in this class is what's called system dynamics modeling. So system dynamics modeling is great for strategic modeling and large scale analysis, thinking about what happens over many, many years, what are the patterns we might get. Whereas if you need to get into more small scale effects, like on a day-to-day basis, how does the operation of a restaurant work from day to day? Those sorts of things, trying to understand things at a much smaller time scale. Then you get into things like discrete event system simulation, which are really not great for the long time scale, but really good for finer time scale. And then if you really need things where you need to simulate, really like it's kind of like a sim world where you actually simulate every single individual in high detail, that's kind of where you get to agent-based modeling. And so there's kind of a continuum of time and space scale here, where if you need a high resolution, need to simulate what every single individual does, in every small space around them, then you can do agent-based modeling. If you need to kind of go up a little bit farther and you don't really care what every individual does, but you care about patterns on small time scales, like from a day-to-day basis, then there are these simulation tools called discrete event system simulation, which are really designed for that. If you're focusing on long-term trends, like month to month to month, year to year to year, then that's kind of where all of these little variations smooth out. That's kind of what system dynamics modeling, or SDM, is designed for, and that's what we focus on in this class. And so there are other opportunities, like there's Marco Jansen teaches courses on agent-based modeling, where he really is focused on, when you put 15 individuals in a room, how do you get them to make a good decision? Well, he can model that using agent-based modeling, the dynamics of person to person. We're focusing more on the group as a whole. How does it behave over a long period of time, not how does each individual interact with each individual, and that's what's kind of down here. So this is just exposure to these other simulation tools, but you don't need to know details of those tools, just know that we're going to focus on one of those tools, but we are not teaching you all of simulation. There are other simulation methodologies which you can zoom in on even finer scales. So kind of to close out here, focusing here on system dynamics modeling, this is kind of a couple of quotes that someone else has written about it. So system dynamics modeling is a branch of control theory, which is for socioeconomic systems and management science that deals with problems of controllability. So it's for analyzing problems in which time is an important factor, and which involves the study of how a system can be defended against or made to benefit from the shocks which fall upon it from the outside world. So it's really less about focusing again on the small scale dynamics of what happens within individuals in a system, but more about how strong and robust and resilient the system is to larger scale forces, things that hit it from the outside, as well as kind of larger scale pressures from the inside, not the random day-to-day things that happen that could happen. So that's kind of, so we're focused on resilience and robustness. And so these models will help us understand causal structures and dynamical patterns. And so we'll be able to say at a large scale, if we notice that groups have usage patterns within them that grow to the sky or oscillate, we can start saying, well, what's going on inside them that tends to lead to these patterns over a long time? And that's what system dynamics modeling is going to help us. So we're going to learn certain causal structures that this is kind of very similar to systems thinking, where you can learn that, well, if we've got coupled feedback loops, we might get S-shaped growth. But we're going to add a quantitative element to that, where we'll say, well, not only do you have coupled feedback loops, but you can have delays. And based on the magnitude of those delays, this S-shaped growth that you might have talked about in other classes can have oscillations. And the size of those oscillations is going to depend on the relative amount of those delays. And that quantitative part of it is something that the simulation really adds over and above what we get from the general systems theory. So that's what we're doing in this class. So that's kind of my introduction to modeling. Any questions of that? Kind of the end of the technical content here. So I've got a reminder of your assignments coming up next, and then an attendance question. All right, let me see if there's questions online. All right, so a reminder here. We have a couple minutes left, but I'm not gonna have you start on this now. I'm sure you'd rather just get out of here, but there is an assignment on mental models. It's a really simple assignment. I'll show you a preview of it on the next slide here. I forget when it's due. I think it's due maybe this weekend. Oh yeah, there, Sunday night. And so this is basically, I'm going to give you 3 images, kind of like we did in class, and ask you questions about what you see when you look at those images. And so it's sort of recognizing your own mental models. Other reminders, don't forget that there's the reading exercise. If you haven't done it already, most people have. The syllabus quiz, you got to get the full 104 out of 104 points to get access to the rest of the class. There's a muddiest point, a weekly muddiest point, sort of the clearest and muddiest things from this week. Make sure to submit that by Sunday. And then we'll be covering chapter 1 on Tuesday. So read through chapter 1 and do the kind of associated readings with that. Just so you know, this is the kind of a quick thing of the assignment that's due on Sunday. Look at this thing, tell me about it. Look at this thing, tell me about it. I'll actually answer the questions that I ask here. say, what direction is the bus moving and justify your choice. And then read this thing and answer this question down here. That is the assignment. Should take you, be very quick, sort of a page worth of work, but it's all submitted on Canvas. All right, so for your attendance question for today, I guess I will ask, when is assignment A2 or this assignment due? So that is your attendance question for today. So go ahead and either go to the URL, scan the code, or if you don't want to do any of that, you can submit this. For those of you at home, you can submit online live right now. For those of you asynchronous, you got 24 hours after I post this video where you can take care of that. So that's the question. When is assignment A2 due? And we will next week actually get into doing a little bit more concrete things like building causal loop diagrams and moving towards building these dynamical simulation models. And that's all I've got for you. So if you've got any questions, feel free to come up after. Otherwise, I hope you have a good weekend and reach out if you do have any questions. Yeah.
So like for the test, is it going to be more like simulation based, or is it going to be like studying like the content based?
I think I've actually got some, if you go into the modules, I think I've got some sample exams from previous semesters you can look over. And it's a mixture of those two. So it's going to cover everything pre-midterm. And so that's going to be, there will be questions generically about kind of the philosophy of modeling. But then there's also, I'm going to show you diagrams and ask you questions about them and maybe effectively have you draw a couple simple ones. I'm not going to ask you specific things about VinSim, like where do you find this in VinSim? But
Okay, yeah.
but I might show you a VinSim diagram and ask you about it.
Oh, okay. Yeah, this is my first like kind of modeling and like theoretical class. So I'm wondering if it's like making the simulation will be like one of the tests.
Well, no, yeah. So the assessing the kind of practical side of making simulations kind of comes out of not the midterm, but it'll be like your final project and some of the homeworks.
Okay.
So that's where you're going to get that practice, and that's where we'll assess you on that. But then like, it's not really practical for me to have you like open up VinSim during a midterm and do that. So the midterm's kind of for the more fundamental thing.
Gotcha. Thank you.
Yep. All right. Any other questions online? If not, I will probably end the meeting. Looks like I only have a couple people hanging on anyway. All right, have a good weekend online.